Hi guys. All right, so for sure, like I said yesterday in my email, the test has been moved to Thursday. That's the latest that I can push it back. So I went ahead and gathered all of the questions that I received tonight, and I'm going to go ahead and do my follow-up video on those questions. Now, I will say a lot of these questions on the review are much more complicated than what you're going to see on the test. So I know some of you guys are stressing out, but if you have done the work, if you have literally worked hard on this review, these review questions are a lot harder than what you're going to see on the test. All right, I'm going to do my best to answer all of the questions we received. I'm praying for you guys, and hopefully I will be back tomorrow. If not, though, the substitute should be able to give you guys the tests. All right, the first questions I got asked were based on pages 174 through 176. That was 3.4. It says in exercises 15 through 18, decide if the situation involves permutations, combinations, or neither. So remember, permutations are where order matters, and combinations are where order doesn't matter. So number 15, the number of ways 8 cars can line up in a row for a car wash. So on this first example, order matters because the way they're lined up is going to make a difference. If you're the first car being washed, it's going to be a lot different than if you're the last car being washed. So this first example, number 15, is an example of a permutation. Oh, I'm using the wrong pen. It's like, why is my pen not working? Because I have like 5 computers out. All right, so that's a permutation. All right, number 16, the number of ways a 4-member committee can be chosen from 10 people. Now, this is just a committee. It doesn't say anything about having ranking. So on this one, order doesn't matter. It just matters which 4 members are being chosen of the 10. So this one is just simply a combination. If they had been given jobs within the committee, like a secretary and a president and a treasurer, then order would matter, and that would make it a permutation. But because they're just choosing members and no ranking is given, it makes it a combination. Number 17, the number of ways 2 captains can be chosen from 28 players on a lacrosse team. Now, this one's a little bit misleading because of the way they asked the question, or because of the way they phrased this. They said 2 captains. Now, think about it. Is one captain going to be over another captain? And the answer is no. Generally, captains hold the same rank. So yes, a captain is a rank, but because they're both the same rank, it doesn't matter who you choose for the 2 captains because they're both going to have the same position. So whenever the positions are the same, like you're giving everyone the same exact job. Same thing like if you had a company choosing vice presidents, your vice presidents, if there's 3 of them being chosen, they would all 3 hold the same ranking. So that makes this one a combination. All right, and finally, I always forget and use this pen and it's super thick. The number of 4-letter passwords that can be created when no letter can be repeated. Now, on 4-letter passwords, you could have something like love. Now, if I take those same 4 letters and rearrange them, like that, is that the same? VOLE. It's the same letters, but it's a different order. So in passwords, order does matter, making these permutations. So hopefully that answered and helped with the questions that I received. How do you know the difference between permutation and combination? You have to think about it, and you have to think about whether or not order matters. All right. The next set of questions I got were based on those same page numbers, 174 through 176, numbers 19 through 21. The directions on these, it doesn't have any directions, so let's just go ahead and read the question. You have 7 different video games. How many different ways can you arrange the games side by side on a shelf? Now, I know we went a lot in depth on our permutation and combination formulas, but this one is just the most basic permutation formula. Because you're taking all of the items, it's just going to be in factorial. So whenever you're not taking a certain number at a time, if you're just taking all of them, you just use in factorial, which would be 7 factorial. And that one works out to be 5,040. If you do 7 times 6 times 5 times 4 times 3 times 2 times 1, you will get 5,040. All right, number 20. 8 people compete in a downhill ski race, assuming that there are no ties. In how many different orders can the skiers finish? Now, again, this is an order or a ranking because first place is going to be different than second place. But all 8 are going to place. You're not taking a specific number. You're not taking like 3 of the 8. You're just wanting to know how many different orders can all of them finish. Because we're using all, it's going to be the same situation. It's going to be, again, in factorial, which is 8 factorial. And if you multiply 8 times 7 times 6 times 5, 4, 3, 2, and 1, you should get 40,320. All right, for the next question, in how many ways can the letters A, B, C, D, E, and F be arranged for a 6-letter security code? Again, you're taking all of the objects, making this the most basic permutation, which is just in factorial. There's 1, 2, 3, 4, 5, 6 numbers. So it's 6 factorial, which is going to give 720 different ways that they can be arranged. The next question I had in that section of 3.4 was numbers 44 and 46. 44, I always do that. It says license plate. In a certain state, each automobile license plate number consists of 2 letters and followed by a 4-digit number. 1, 2, 3, and 4. Okay. How many distinct license plates numbers can be formed if A, there are no restrictions? So if there's no restrictions, well, you have to ask yourself, how many letters are there? There's 26. So each letter would have 26 possibilities. And remember, to find the total number of outcomes, you multiply the number of possibilities together. So it'd be 26 times 26. Now, if we look at the 4 numbers, numbers can go all the way up from 0 to 9. Those are our 1-digit numbers. There's actually 10 of them. And that would give us a total for A. You see my answer. Number 44A should be 6,760,000 possible license plates. All right, for part B, we're going to be restricted just a little bit. The part B, it says, let's see. Sometimes it'll let me move it, sometimes it won't. All right, B. The letters O and I are not used. So instead of having 26 letters, if we can't use O and I, that drops us down to 24 letters. So it's going to be a very similar number, just a little bit smaller because we're missing those two numbers. And, not going to let me. If we go ahead and multiply those numbers together on part B, we should get a total of 5,760,000. All right, part C. What is the probability of selecting at random a license plate that ends in an even number? Now remember, probability is parts out of the whole. We already found the whole, and that was the 6,760,000. I can't write. 760,000. That was the whole. We want to know what's the part. So they've limited us on number 44C because it says, what's the probability of selecting at random a license plate that ends in an even number? So we would go ahead and change this. I'm going to change it back to 26 because they're not limiting us on the letters anymore. But they are limiting our last number to just the even numbers. Now, how many even numbers are there? There's 0, 2, 4, 6, and 8. There's 5 even numbers. Now, if we were to write the bottom out, it would have been 26 times 26 times 10 times 10 times 10 times 10. Now, what you could do without even multiplying them out is you would notice there's the same thing on the top and the same thing on the bottom, except for the last number. So again, if I had left this, the total number of possibilities that we found from part A was 26 times 26 times 10, 10, 10, and 10. And remember, probabilities parts out of a whole. All of these end up canceling out, leaving us with 5 out of 10 or just 1/2. And if you want to check that just to confirm, you could multiply 26 by 26 by 26, 26 by 26 by 10, by 10, by 10, and by 5, and you would get exactly half of that number. And when you divide them, you would get 1/2 for your probability. So again, probability is parts out of a whole. The whole we found for part A, those were all of the possibilities. And then when we limited it to only even numbers, that made the last number 5 out of 10. And when we divided those two probabilities, it gives 1/2. All right, the last question from that section that I had was number 46. It's a question on area codes. It says, an area code consists of 3 digits. How many area codes are possible? A, if there's no restrictions. So this is the same idea. So on A, there's no restrictions, 3 digits. There's 10 one-digit numbers. So that would be 10 times 10 times 10, which would give 1,000. Possibilities for A, for area codes. For part B, the first digit cannot be a 0 or a 1. So that limits us by 2 numbers. So it's 8 by 10 by 10. Very similar. For part B, we're going to get 800. And part C, they love questions like this. What is the probability of selecting an area code at random that ends in an odd number if the first digit cannot be 1 or 0? So they're limiting us to B. It says the first number cannot be 1 or 0. So we already know all of our total possibilities are going to be 8 times 10 times 10, which was 800. But they're limiting us. They want to know the probability of selecting an area code at random that ends in an odd number. So the first digit can't be 1 or 0. The second number can be anything. And the third number ends in an odd number. There's 1, 3, 5, 7, and 9. There's 5 possibilities. And again, we have a very similar situation to what you saw above. The 8s and the 10s would cancel, leaving us with 5 over 10, which is the same thing as 1/2 or 0.5. So our probability of that happening for part C would be 0.5. I don't know why the book likes to ask those questions. I think they ask that 3 or 4 different times in this section of homework. All right, that's it for pages 174 through 176. The next thing we're going to look at is we're going to go back to the review, and I'm going to answer the questions that were posed on the review. And I've gone ahead and highlighted them to make them easier for me to find. All right, so I was asked more on questions 1 and 2, and I was asked if there was another way besides the tree diagram to find all of the sample space. And the answer to that is yes, you can think about it, but if you have a large sample space, sometimes a tree diagram can help you to think out all of the possibilities. I believe the first question on the test, you can do a small tree diagram to find all of the possibilities in the sample space. So it is helpful. And the other helpful thing is just using the fundamental counting principle. So like if we look back at number 1, it says identify the sample space and determine the number of outcomes. So to determine the number of outcomes, you multiply the number of possibilities in each case. So we're tossing 4 coins. So the first coin has 2 outcomes, heads or tails. The second coin also has 2 outcomes, heads or tails. The third one has 2 outcomes, heads or tails. And the fourth one has 2 outcomes, heads or tails. And if we multiply 2 times 2, that's going to be 4. Times 2 is 8, times another 4 is 16. So that's going to give 16 possible outcomes for that. But again, I would say the tree diagram is one of the easiest ways to write them all down if you don't want to think that hard about trying to find out all of them. But 16 outcomes is not that many to think up. When you get more of like 36 outcomes, it gets very confusing and a lot more difficult to think of all of the possibilities. All right, for question number 2, this one, rolling 2, and actually I didn't write them out, and I don't know if you guys want me to write them out, so I guess I should probably do that. So let's go ahead and do that for this one. So for the first one, you could have flipped heads or tails. For the second one, heads or tails. Don't mind that I'm going on the space of the other tree diagram. Heads or tails, heads or tails, heads or tails, heads or tails. And so let's see, we have 1, 2, 3 coins. We need 1 more coin to flip. And finally, to write the sample space, you would start at the top. So we'd have heads, 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 and heads. Oh, my pen does not like to make that middle line. Then we could have heads, 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 and tails. Then we could have heads, heads, tails, heads. And heads, heads, tails, tails. Now, I'm not going to write all of these out because I need to explain more, but just to show you how you would read that, you start at the first and then go down each branch. All right. Let's see, moving on, I want to make sure, okay, for number 2, I was asked to actually find the probability of it. So yesterday I showed you guys how to, on that one, the probability of rolling a 6-sided die. We looked at what the book had given for the answer, but someone wanted to know the probability of getting a sum of 4 or 5. So we need to know the number of possible ways that you can get a sum of 4 or 5 divided by the total number of ways. So here I circled all of the 4s or 5s. There was 1, 2, 3, 4, 5, 6, 7 ways that we could get a 4 or 5. So the probability of a sum of 4 or 5. There were 7 ways to make the outcome we wanted out of a total of 36. And if we divide that, it gives 0.194 for our probability of that happening. Now again, the one on the test that you have to do the tree diagram for is not big like this. It's way smaller. So I would not give you one this big to actually write the sample space out for. I don't even want to do that. I would definitely not make you guys do that. Again, like I said, some of these questions in the book are so much more complicated than what you're actually going to see. So if you're doing good on most of these, you're fine on the test. All right, next question that I had a question on is number 26. So we're going to go down to 26. And this is the one that I worked on yesterday. So this was asking whether or not they were mutually exclusive. So I guess probably the question why they're not mutually exclusive. And the reason for that is because you can love cats and you can own a dog. So let's get a situation. So let's say you are okay, let's use my sister-in-law Sarah as an example. She absolutely loves cats to death, but when she first got her condo, she ended up getting a dog. So she loves cats, but she owned a dog for a short time because she ended up getting rid of the dog. But she was one of those people who was a cat lover who owned a dog. Now, if you were to map her and other people in the area, she would be here in the cat lovers, but she also owned a dog. So she would be in the mix of both of those. She would not, that's not mutually exclusive because you can love cats and own dogs. So mutually exclusive is just asking, is it possible to be both? If it's possible to be both, then it's not mutually exclusive because you're going to overlap in 2 different segments. All right, next question that I got was question number 29. So let's go ahead and look at that one. All right, so let's read the question. A random sample of 250 working adults found that 37% access the internet at work, 44% access the internet at home, and 21% access the internet at both work and home. So this has already told you that it's not mutually exclusive because you've got people in the overlap who are accessing the internet at work and at home. It says, what is the probability that a person in this sample space at random accesses the internet at home or at work? So, and I also had someone ask And I'll have to look at the question again, at home or work. So we're going to add our probability at home, we're going to add our probability at work, and then we're going to subtract out the overlap. So I had a question someone asked me, how do you know when you find probability and when to add? Well, answer to that is, oops, I didn't do that every time. Answer to that is the word or. When you're finding an or probability, you're going to add the probabilities together. So you know that you're still finding probability, but you know to add when you see the word or. When it's probability, but it asks for or, you're going to add. Only difference is sometimes you'll have to subtract out the overlap if it's not mutually exclusive. So first, let's do the probability of at home. I don't know why I wrote it like that. I wrote it backwards, but 44% access it at home. So it's going to be 0.44. 37% access it at work. So it's going to be 0.37. But then there's also the people who access it at both. So we're going to have to subtract out the 0.21 because if we don't, it's going to count that twice. They're going to be double counted. So when we go ahead and add and subtract our numbers for number 29, we get 0.60. So 60.6 access the internet at home or at work. All right, number 31. A card is randomly selected from a standard deck. Find the probability that the card is between 4 and 8 inclusive or is a club. So again, here's another or problem. Or tells you you have to add and you multiply. So when it's probability or add, probability and multiply. So we would need to know how many possible cards are there that fit this criteria. When it says inclusive, that means including. So it means including 4 and 8. So between 4 and 8, or is a club. So let's go ahead and break this down. 4, 5, let's write it down. 4. Gosh. Sorry, guys. Let's try that again. 4, 5, 6, 7, 8, right? So inclusive means it's all 5 of those cards, but how many suits are there that have a 4 through an 8? Well, hopefully you said there's 4 different suits. So there's going to be 4 sets of 4, 5, 6, 7, 8, making that a total of 20 cards. So the probability of being between 4 and 8 or a club, very mathy way to write that. We just said there's 20 cards that are between 4 and 8 because there's 4 suits. So there's 20 out of a total of 52 cards. Then if there's 4 different suits and club is one of the suits, there's going to be 52 divided by 4. There's 13 cards that are clubs out of a total of 52. But we know that some of those cards are going to be 4, 5, 6, 7, and 8 of clubs. So there's 5 cards that are going to overlap. And those 5 cards are the 4, 5, 6, 7, 8 of clubs. You're counting them twice. So we do have to subtract out 5 cards out of the total of 52. So when we go ahead and do that, that's going to give us 28 out of our 52. And for number 31, we're going to get an answer of 0.538. So hopefully this is helping. All right. Next question I had, we are going to, as I make marks all over my page. Next question, 2931, was 53 and 54. And I didn't go over these at all yesterday, so let's go ahead and take a look at them. So for 53, it says, in a state lottery, you must correctly select 5 numbers in any order out of 40 to win the top prize in any order. How many ways can 5 numbers be chosen from 40 numbers? All right, so for this question, all right, sorry, so I realized that I copied the wrong question, so I had to go back in and recopy. So I got it recopied, and let's go ahead and go over number 53 and 54. I'm glad I checked that. All right, a batch of 200 calculator contains 3 defective units. What is the probability that a sample of 3 calculators will have no defective calculators? So, all right, if there's 200 calculators, and we want to know the probability that all 200 are not defective, what we would do. All right, so for this one, a batch of 200 calculators contains 3 defective units. What's the probability that a sample of 3 calculators will have no defective calculators? Well, first of all, we need to know the probability of having one that is not defective. If there's 3 defective units out of 200, that means 197 of them are not defective. And let me fix that. If we go ahead and divide that 197 by 200, I get approximately 0.985. So that's undefective. Now, if we have a sample of 3, the first one is going to have a 0.985 probability of not being defective. The second one is going to be the same. So on that one, and something I thought of, it's not quite going to be the same, because the first one, if it was not defective, we've taken it out without replacement. So the first one was 197 out of 200. Then we take another calculator out. So now instead of 197 non-defective, we took one of the non-defective out, making it 196 out of 199. And finally, if we take one more working calculator out, there's going to be 195 out of 198. Now you would go ahead and use parentheses and multiply 197 times 196 times 195, then put a division symbol, and then use parentheses again, 200 times 199 times 198, and we get 0.955. So that's not going to be unusual to have all 3 samples be perfectly working calculators. For part B, all defective. Now this is going to be a lot more surprising if all 3 of them are defective, because there's only 3 in a batch of 200. But this one is going to have the same idea. So if they're all defective, you are going to start with 3 defective calculators out of 200. That's the first one. Or the second one, you've already taken a defective one out, so there's 2 defective ones left out of 199. Finally, for the third one, there's 1 out of 198. Now to multiply this, you do 3 times 2, which is 6, and then you multiply the bottom numbers in parentheses, 200 times 199 times 198, and when you divide them, you get a very small number. In the calculator, it says 7.61 times 10 to the negative 7, which is 6 zeros, a decimal point, then 6 zeros, then 761. So that would be very unusual. Again, that number is 7.61 times 10 to the negative 7. It's a very small number, and it would be very unusual for you to get all of the defective calculators. For parts C and D, I'm not sure if you guys wanted C or D. It says at least one defective calculator. That could be one defective, that could be two defective, or that could be all three defective. So on problems like this, I like to do the complement, and I would do 1 minus the probability of none, which we already found. Probability of none is 0.955. And if we subtract that, we have 1 minus 0.955. We get 0.045, and that would be unusual because it's such a small number. So let me move this over so I can write the answer. Again, that's unusual. And final question, the probability, so that was for part C. The probability of at least one non-defective calculator. So for this one, at least one non-defective, so that's one non-defective, two non-defective, or all three non-defective. That is going to be the opposite of what we did back in B, which was 7.61 times 10 to the negative 7. You would take that number from 1. So it'd be 1 minus 0.000000761. And that would give us 0.99999999239, which would be not unusual. So for that one, again, it's the opposite of the all defective would be at least one non-defective. So you would take 1 minus that answer from this part, and that would give you basically 0.999. All right, and finally, number 54. Let me look on my paper because I think it was asked, parts C and D for number 54. A batch of 350 raffle tickets contains 4 winning tickets. You buy 4 tickets. What is the probability that you have no winning tickets? So let's just find our basic probability first, so we can use that to calculate our numbers. And I'm going to do those because we're going to need those numbers for part C and D anyway, so I'll do an A and B. So there's 4, so probability of winning is 4 out of 350. And if we divide 4 by 350, we get 0.114. And the probability of losing, which is going to be the opposite of that, it's going to be 346 out of 350. It should be the other side of that number. 346 divided by 350 is 0.989. It's not going to add up to make exactly 1 because I have rounded. So just keep that in mind. All right, so for part A, we're buying 4 tickets and we want to know the probability of no winning tickets. So our probabilities are going to go down. So no winning tickets means they're all losers. So for the first one, none of 4, probability of none of 4 being winning is going to be first 346 out of 350. Then we take 1 ticket out, one of the losing tickets, so 345 out of 349. Then 344 out of 348. Finally, 3 losing tickets out of 347. When you do this in your calculator, again, guys, use parentheses when you multiply it out the top and the bottom. And on that one for A, we should get, let's see, that's number 54. We should get 0.955. So I'll go ahead and check myself. All right, and we're good. So for part B, all of the winning tickets, this is going to be very unusual. So our probability of winning, we're going to use this right here. So for B, probability all of 4 are going to win. So all of 4, we start with 4 winning tickets of 350. If we take a winning ticket out, then there's going to be 3 of 349, then 2 of 348, then 1 of 347. And when we multiply it out, we would get 0.005. So that one would be way unusual. And I realized I looked at the wrong number, guys. I was like, wait a minute, that's a little bit high for what it really should be. And I went ahead and calculated it. And it's 1.63 times 10 to the negative 9. So it's a very small number. It's like 8 zeros. And if we round it up, it would be, you could round it to a 2. So 0.0, you do 8 zeros, 2. So it's going to be a very small number. In scientific notation, it's about 1.6. You could round that to 2 if you wanted to, times 10 to the negative 9. It's a very unusual number. All right, C, here's where we're going to use our complements. Probability of at least 1 winning. The complement of that is the probability of none winning. We said the none winning was 0.955. So for part C, we'd get 0.045. And for part D, probability of at least 1 non-winning ticket is going to be the opposite of probability of at least 1 non-winning is going to be 1 minus the probability of all of the 4 winning, which is 1 minus 1.6 times 10 to the negative 9. That was that very, 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 very small number. And if we subtract that for part D, it's going to give us like 0.99999. I think we should have 8 of those. 1, 2, 3, 4, 5, 6, 7, 8. There's 7 or 8, and then an 8. So it is not unusual. All right. I just got a question or a request for number 33. So let's go ahead and look back at number 33. I will check this one more time too, just to make sure that I get all of the questions that you guys have asked me tonight. It is getting late, so I'm tired, so I do apologize. We're at number 33. A 12-sided die numbered 1 to 12 is rolled. Find the probability that the roll results in an odd number or, so let's see, probability, roll odd or a number less than 4. So for this one, should we take it as they're not putting it back in? Oh, so for number 33, there's no need to worry about replacement because every time you roll a die, it doesn't, it's not that it's not replaced, it's all those numbers are still going to be there. Every single time you roll it, all those numbers stay there. So for number 33, let's go ahead and do that question. So if it's 12-sided die, we're going to have half of those numbers be odd. So the probability of it being odd is going to be 6 numbers out of 12. We're going to have 1, 3, 5, 7, 9, and 11. Then remember, or probability you add, we're going to add to that a number less than 4. What numbers are less than 4? Well, there's 3, 2, and 1. So there's 3 numbers out of 12. Now you could do this one of 2 ways. You could say, but wait a minute, Mrs. Vetter. We were talking about the odds. 1 and 3 are both odd, and we've already counted it. So we would only count one of those 12 numbers. So you could do it that way, or you could just subtract out those 2 odd numbers at the end. So the ones that are both odd and less than 4 with the numbers 1 and 3. So there were 2 numbers that were counted twice. So you could do it either way that makes more sense. When we add and subtract, we get 7 out of 12. And for number 33, that one should give us 0.583. All right, I'm gonna do one more sweep and make sure that I have answered everything. All right, guys, it looks like I have answered all of the questions. Hopefully that helps. And just, again, this review is a lot harder, in my opinion, than what the actual test is. So if you have a basic understanding of the topics, you'll do fine. None of the questions are going to try to trick you, I don't believe, or in my estimation. All right, guys, I'll be praying for you, and hopefully I will see you guys soon. Have a great day. Vetter out.